So in this short film we will look at the Nobel Prize in Chemistry for the year 1909, awarded to Wilhelm Ostwald for his work on catalysis, for his investigation into the fundamental principles governing chemical equilibria and rates of reaction. Here you see a beautiful illustration. This is his Nobel Prize diploma. All winners receive such a diploma, and they're always beautifully decorated, as you can see. Here you see one of his setups he used to create nitric acid, starting from ammonia, this so-called Ostwald process. Okay, here's some information from the official Nobel Prize site. Here you see where it's coming from. In the 19th century, chemists noticed that certain chemical reactions seemed to be caused by substances that remained unchanged in the process. In the 1880s, Wilhelm studied the speeds of numerous chemical reactions, including reactions occurring in the presence of acids and bases. In 1894, he revealed what happens. A substance, as a catalyst, can affect a chemical reaction speed, but is not included in its end products. This understanding shed great light on chemical reactions occurring in both industrial processes and living organisms. Then some biographical information also from the Nobel Prize sites, summarized by me. Ostwald started his experimental work in 1875 with an investigation on the law of mass action of water in relation to the problems of affinity, with special emphasis on electrochemistry and chemical dynamics. In consequence of his pioneering work, especially in the field of electrochemistry, which also led to the discovery of the law of dilution named after him, his activity as a writer and his gift for organization, Ostwald became one of the founders of classical physical chemistry. He published numerous textbooks, numerous other scientific works on analytical chemistry, electrochemistry, inorganic chemistry followed. Ostwald also founded and edited the Zeitschrift für Physikalische Chemie in 1887. Ostwald himself edited 100 volumes up to 1922. He was also in charge of the organization of the Department of Physical Chemistry at Leipzig University. In 1894, he founded the Deutsche Elektrochemische Gesellschaft, German Electrochemical Society, which in 1902 expanded to become the Deutsche Bunsengesellschaft für angewandte physikalische Chemie, translated German Bunsen Society for Applied Physical Chemistry. After his retirement in 1906, Ostwald founded a new sphere for his scientific and organizational talents. Besides continuing his studies and publication on philosophy, such as Der energetische Imperativ, the energetic imperative, moderne Naturphilosophie, modern philosophy, the Pyramide der Wissenschaft, the Pyramid of Science. He also took an active part in public life. He supported the middle-class pacifist movement, was interested in educational reforms and in monism. He believed, in view of his position, he could decisively fight the church's claim to power in the field of natural sciences and to spread a modern scientific ideology. This aim he pursued in his writings Monistische Sonntagspredigten, monistic Sunday sermons, and Arbeiten zum Monismus, work on monism. In 1902, Ostwald founded the Annalen der Naturphilosophie and edited 40 volumes up to 1921. He also founded Klassiker der exakten Wissenschaften, that's classic for exact science, in 1889, of which some 215 volumes have been published. Right up to the end of his life, Ostwald studied colors and shapes in the endeavor to find a specific standardization for colors. His main works in the field are the Farbenfibel, the color primer, die Van Leer, color theory, die Harmonie der Farben, harmony of colors. He also published a periodic called Die Farbe, color. Well, again, this is coming from the official site, the Nobel Prize. Here you see the link. As said, slightly summarized by me, but if you want a complete information, follow the link. Here again, you see the reaction for which he got the prize. One of them. He got it for catalysis. Here you have in that a process in which catalysm is important. You start with ammonia and you end with nitric acid, and this is called the Ostwald process. Then a award ceremony speech by Dr. Hildebrand. Again, summarized by me shortly for a bit. As early as the first half of the last century, it had in certain cases been observed that chemical reactions could be induced by substances which do not appear to participate in the reaction themselves, and which at all events were not altered in any way. This led Berzelius, in his famous annual report on the progress of chemistry for 835, to make one of his not infrequent building conclusions, whereby scattered observations were collected in accordance with a common criterion and new concepts were introduced in science. He termed the phenomenon catalysis. However, the catalysis concept soon became up against opposition from another eminent quarter as allegedly unfruitful and gradually fell utterly into discredit. So 50 years later, Wilhelm Ostwald carried out a number of studies to determine the relative strength of acids and bases. He sought to solve this extraordinarily important matter for chemistry in a variety of ways, which all yielded consistent results. Amongst other things, he found that the rate at which different processes take place under action of acid bases can be used to determine the relative strength of the latter. He performed extensive measurements along these lines, and in doing so laid the foundations for the entire procedure for studying rates of reaction, all the more essential typical cases of which he examined. From that time onwards, the theory of the rate of reaction has become increasingly important for theoretical chemistry. These tests, however, were also able to throw new light on the nature of catalytic processes. After Arrhenius had formulated his well-known theory that acids and bases in aqueous solution are separated into ions and that their strength depends on their electrical conductivity, or more accurately, on the degree of dissociation, Ostwald tested the correctness of this view by measuring the conductivity and hence the concentration of the hydrogen and hydroxyl ions with acids and bases which he had used in his previous experiments. He found Arrhenius' theory corroborated in all of many cases which he himself investigated. His explanation that he consistently found the same values for the relative strength of the acids and bases, whichever method he used, was that in all these cases the hydrogen ions of the acids and the hydroxyl ions of the bases acted catalytically, and that the relative strength of the acid and bases was determined solely by their ion concentration. Ostwald was hence led to undertake a more thorough study of catalytic phenomena, and he extended its scope to other catalysts, as they were called as well. After consistent continuous research, he successfully formulated a principle to describe the nature of catalysis, which is satisfactory for the present state of knowledge, namely that catalytic action consists in the modification by the acting substance, the catalyst, of the rate at which a chemical reaction occurs, without the substance itself being part of the end products formed. The modification can be an increase but also a decrease of the reaction rate. A reaction which otherwise proceeds at a slow rate, taking perhaps years before equilibrium is attained, can be accelerated by catalysts to such an extent that it is complete in a comparatively short time, in certain cases with 1 or a few minutes, or even in fractions of a minute, and conversely, the rate of a reaction is a measurable parameter, and hence all parameters affecting it are measurable as well. Catalysis, which forms appear to be a hidden secret, thus has become what is known as a kinetic problem and accessible to exact scientific study. Ostwald's discovery had been profusely exploited. Besides themselves, a large number of eminent workers have recently taken up this field of study, and the work is advancing with increasing enthusiasm. The results have been truly admirable. The significance of this new idea is best revealed by the immensely important role, first pointed out by Ostwald, of catalytic processes in all sectors of chemistry. Catalytic processes are a commonplace occurrence, especially in organic synthesis. Key sections of industries such as sulfuric acid manufacture, the basis of practically the whole chemical industry and the manufacture of indigo, which has developed so during the last 10 years, are based on the action of catalysts. A factor of perhaps even greater weight, however, is the growing realization that the enzymes, so-called, which are extremely important for the chemical processes within living organisms, act as catalysts, and hence the theory of plant and animal metabolism was essentially in the field of catalyst chemistry. As an illustration, the chemical processes involved in digestion are catalytic and can be simulated step by step using purely inorganic catalysts. Furthermore, the ability of various organs to transform nutrients from the blood in such a way that they are suitable for the specific task of each organ can indubitably be explained by the occurrence of various kinds of enzymes within the organ capable of catalytic reactions adapted to their practical purposes. That apart, it is changed that such substances as hydrocyanic acid, uric chloride, hydrogen sulfide, and others which act as extremely potent poisons in the organisms have also been observed to neutralize or poison even pure inorganic catalysts such as, for instance, finely dispersed platinum. Even from these brief references, it would be clear that a new approach to the difficult problems of physiological processes has been possible with the aid of Ostwald's theory of catalysis, because they are related to the actions of enzymes in the living organism. The new field of research is of an importance for mankind that cannot as yet be fully gauged. Okay, this was the summary of the award ceremony speech, as always coming directly from the Nobel Prize site. You see the link, but summarized by me. If you want a complete ceremony speech, read it, then follow the link. Here again, some illustrations of the Ostwald process. Seen it before. Here in more detail, you put ammonia into the process, and at the end you get nitric acid. Here again, another picture about the same process. You see the nitric acid coming out. You see the ammonia going in. Okay, this is it for this time. Next time, that is next week, we will go again into this Nobel Prize for Chemistry, then with the lecture given by Oswald himself. For now, thank you for watching, and may I see you at another time with another Nobel Prize for Physics, Chemistry, or Medicine/Physiology.